Morning guys, I'm going to make a quick video on looking over the end of topic 5 test that you did in Scholar on intermolecular forces. So the first question was, London dispersion forces of attraction are a result of what? Now if you remember back to my previous video on YouTube about London dispersion forces, I'll just show you. If you think of an atom, okay, and a neighbouring atom, the London dispersion forces are the attraction between a temporary dipole and an induced dipole. And a temporary dipole, remember, is where the electrons wobble to one side of the atom, causing that side of the atom to become negatively charged. And then if this atom meets a neighbouring atom, because this side is negatively charged, it repels the electrons in the neighbouring atom to the other side. Okay, so this is your temporary dipole. Okay, and it causes an induced dipole on another atom. Okay, so back to the question. They're a result of a temporary dipole causing an induced dipole. So, where are we? That one there. Okay, moving on to question 2. Which of these is the strongest? Okay, so you need to remember that intermolecular forces, the ones between molecules, are always weaker than intramolecular forces. So if I show you an example, if you think of, I'll just do hydrogen fluoride because it's easy. So if you think of hydrogen fluoride molecules, the bond within the molecule, the intramolecular bond, would be a covalent bond because you've got two non-metals. Okay, and remember your intermolecular forces, well in this case you've got H's and F's, so it would be hydrogen bonding. Okay, now if you think of hydrogen fluoride, if you think of it as a liquid just now, okay, if you wanted to turn hydrogen fluoride into a gas, you're not actually breaking up the molecules, you're not breaking the covalent bonds, you're only breaking the weaker hydrogen bonds between the molecules, because remember, turning a liquid to a gas, the molecules in a gas are further apart than they are in a liquid. Okay, so in a gas, your hydrogen fluoride molecules would be much further apart and the forces between them would be much weaker. Okay, so thinking about the strength, covalent bonds are the strongest, then you've got your hydrogen, then you've got your PD-PD, then you've got your LDF. Okay, so which is the strongest? Covalent bonds. Right, on to number 3. What is the connection between the size of molecules and the London dispersion forces of attraction? Right, if we think of, just thinking about diatomic molecules, right? So if we think of hydrogen, a hydrogen molecule, okay, and if we think of a chlorine molecule and compare them. Now, if you think back to the London dispersion forces, they're the attraction between a temporary dipole and an induced dipole, and it's all to do with the movement of the electrons, right? So when you're thinking about London dispersion forces, the more electrons there are, the stronger the dipoles, therefore the stronger the London dispersion forces. So if you think of hydrogen, a hydrogen molecule, looking at hydrogen, hydrogen's got 1 electron. So in a hydrogen molecule, you've got 2 electrons. In a chlorine molecule, chlorine's got 17 electrons. But because it's diatomic, 17 times 2 is 34 electrons. Okay? So, what is the connection between the size of molecules and the London dispersion forces? The bigger the molecule, the more electrons it's got, so therefore the stronger the London dispersion forces. Just remember that. So that would be... where are we? The smaller the molecule, the weaker the force. Moving on to to number 4. Which of these molecules has the largest permanent dipole? Well, the largest permanent dipole is just the biggest difference in electronegativities. So you should have got HA for that one, because remember, fluorine's got the biggest electronegativity out of all the elements of 4 and hydrogen's 2.2. Okay, so just the biggest difference. Moving on to 5, identify the trends which would occur in descending the elements of the halogen group. Right, so if we look at the halogens, the first one it says is the covalent radius decreases. Now the covalent radius just means how big the molecular atom is. So looking at group 7, the halogens, as you go down the group, you'll see that one more electron shell has been added each time, so therefore the size of the atoms is increasing. So therefore the first one's wrong, because the covalent radius would increase. Secondly, the London dispersion forces become stronger. Well, if we remember from the previous question, if the London dispersion forces are strong, that means there's a lot of electrons. That means the size of the atoms or molecules are getting bigger. So your halogens, remember, are made up of the diatomic molecules. So fluorine molecule would have 18 electrons, chlorine would have 34, bromine would have 70, etc. Okay, so the size of the molecule is increasing, there's more electrons, so therefore the second one is correct, the London dispersion forces become stronger. Third one down, the relative atomic mass increases. Well, the relative atomic mass, remember the mass of an atom or molecule is down to the number of protons and neutrons it's got. So there's your protons, 9, 17, 35, 53, etc. So the mass would increase as you go down the group. Okay, so that is correct as well. The electronegativity increases. Well, if you remember your definition of electronegativity, it's the attraction an atom has for bonding electrons. And bonding electrons are only the outer electrons. Okay, so we're thinking, well, what happens to the attraction of an atom for the outer electrons? Okay, so if we think of our molecules, fluorine, chlorine, bromine, iodine, I'll just draw it here. So fluorine, okay, fluorine has 2 electrons in its first shell and 7 in its outer shell. Okay, and then your chlorine is 287. Okay, now we'll just look at these two. So that's fluorine and that's chlorine. Okay, now the electronegativity is the attraction of the atom for the bonding electron. So the attraction for this electron here, well, this electron is near the inner shell, okay, because it's only got 2 shells, whereas chlorine's got 3 shells, so this outer electron is further away from the nucleus, so that means there would be less attraction. Okay, so going down the group, the more shells are increased, the further away the outer electrons are. Therefore, the electronegativity decreases. There's less attraction for that outer electron because it's getting further away from the nucleus. So that one's wrong. And then lastly, the boiling point, it decreases. Well, boiling points and melting points are affected by your intermolecular forces. Okay, and thinking about group 7, your halogens, well, they're all non-polar, so they would have London dispersion forces between the molecules. So if you wanted to melt or boil any of these molecules, you're only trying to break London dispersion forces. So just think, what affects London dispersion forces? The number of electrons or the size of the molecule. So we know that as we go down the group, the size of the molecules gets bigger and the number of electrons gets bigger as well. So the London dispersion forces would increase. So therefore, as you go down the group, the melting and boiling point would also increase. So that last one is wrong. So your correct ones are those two there.